我强烈要求就用这个封面，不要用螃蟹画的那个，我特别要求。
好了 ，testing。OK， 没事，not important。姓黄啊，黄。Okay, hello, testing. Okay, so there's some time frame here to take note here. So first of all, I accidentally put your assignment deadline in the wrong week, right? Should be week 6, but become week 7. So you guys prefer to keep the current one? Okay, so if you're gonna keep the current one, I think we will adjust the assignment 4, but I think I will still release the assignment for this week on Friday. Yeah, so you have to start first. Better. Okay, better you start first. Second is replacement. So there's a replacement for your Diwali holidays. So do you guys want to replace on next Tuesday or the following week? So if you replace on the next Tuesday, that means it's the same week as your Diwali holiday. So you take 2 class on Tuesday, then done for the week. Or we move to the next week, then there will be 3 abstract algebra on the same week. So we do it next week, okay? Okay, so we just do it next week. So this one we move to 1st November, but I will still release the assignment 4 on this Friday, so you can start and look at it first. 1st November, right? Is it 1st Friday? Next Friday. And then the revision week, I think we fix on week 8, week 8 Monday, 6 to 8. Okay? Yeah, revision or revision class. Okay or not? Monday, 6 to 8. Yeah. I think only night time everyone is free. Last time we asked about this free time. Okay, if okay, then I will start booking. And then midterm will be on Thursday, 5 to 7. I go and book a better room. Okay? A proper classroom. Which one? This one, you mean this one? 7 to 9? Why not 6? Got class. Class. Oh, got class until 6. Okay, we can do 7 to 9. Some of you got class to 6. Yes. I don't know whether this depends on, depends on how long we discuss. I was thinking 6 to 8. If you want to go longer, maybe go to 9. But if we go longer, also can go to 10. I mean, depends. So we just fix 2 hours first. Yeah. 7 to 8. So during this revision, so please do your tutorial question first. Okay. And then I think Camping also put out some additional exercises. Okay. Hey, did Rachel and Hao Tian try asking question or not? You guys try? No try. Okay. Sorry? The chapters? Other chapters. The front one is never try. Sorry? Galleon. Okay. Galleon is which one? Oh, that one. Galleon. Oh, okay. I don't like Galleon because not rigorous. Yeah. I'm not sure about the question, but at least the content there. I prefer the Artin and Jackson one. Artin and Jackson. Okay, another thing is, hey, do you know why other teacher give you cover page? For example, property. Why? Why you guys use cover page? You know, for assignment or project? Don't know. Huh? To what? Cover the page. To cover the text. Well, things. What do you need to write on the cover page? Name. What else? Student ID. What else? Maybe mark given by me. Okay. So actually, I don't like this cover page thing. So I try to avoid. But you also avoid putting your name down. Okay. So I want you to put your name and ID on your assignment each time you submit. Okay. And we have to do resubmission now. So meaning your assignment one, right? Go and download my feedback. If you didn't put your name down, go and download my feedback, write your name, and then upload again. So where do you upload? Don't upload to the old link. I put out a new link there. So let me open it for you. Because I never met this kind of problem before, you know. Even though I don't give cover page, they will write their name. But your class, most of you didn't do it. So a bit dangerous. It's very dangerous. Okay, so if you go to this Moodle, right? Okay, and then I will put this assignment one with name and student ID added. So please, okay, what do you do? Download your feedback file, add your name in, submit again. Does it make sense or not? Okay, don't submit to the wrong one. Don't submit to the previous one. I supposed to close this submission already. You supposed not to submit here again. Okay, submit to this new one. Does it make sense? OK， 全部人听得懂吗？下载你的 assignment one 的 feedback， 加上你的名字和 student ID， 交多一次在这里 ，OK 吗？啊？不是 rename， 就是你交的那一份东西里面要有你的名字和 student ID，OK 吗？我有哦。啊，有的就不用哦。加上去罢了，加在某个空位里面。啊，加罢了。OK， 加不了。因为那时候我以为只有几个没有，结果注意看一下，结果好像几乎都没有。几乎都没有，所以有点危险。如果因为 because we need to submit this marking sample to this MQA for them to like check the courses, so they might be finding trouble. Okay, so you download your feedback file, add your name, submit again. Okay. Make sure you use the feedback file because we don't need to remark again. Just add it on and then put it back here. It will be the same for assignment 2. Okay, after I hand it back to you, the assignment 2, and then you should do the same thing. So hopefully for assignment 3, add your student name and student ID. And to do this, I have changed your file. So I add the 2 columns there to remind you. Okay, so if you download the latest assignment 3, right, you will see name and student ID here. Okay. Yeah. Okay or not? Okay. So please do your assignment 1. Please download your feedback file, add your student name and student ID, and then submit again. Okay. Does it make sense? Okay. If you forgot, please your friend ask you to do. Okay, ask your friend to do it, and then I will chase after you. I think I don't want to like, cut off your mark there here, no use one, because the point here is I want you to add the add the name in. It's not that I auto your mark, your name will straight away appear. It's not like that. So 我觉得我们要做一件事情，就是说要让大家自动自发，我们不要设太多条条框框啊，或者什么规则。我们说的社会应该要是自动自发的。We have to be we want to be how to say take initiative. Okay, we need to learn to take initiative, learn about your responsibility. Okay, it's useless that I keep punish you. Even if I keep punish you, you don't know it's also useless. You know, I take off your 5 marks, you still don't put your name there. What's for? The 5 marks, I'm not for me one. You understand about? So once you understand, you will keep remember one. I don't need to remind you. I don't need even to punish you. Does it make sense or not? So why you need to put your student name and ID? Do you know? You know why? Do you know why? Because if you pass this document randomly to other person, how do I know check? How do I check your ID? How do I check your student name? How do I know who this guy is? So at least you write it on your paper. Does it make sense? Okay. It's not belong to a random person. And maybe you'll say, oh, PDF file, there's a name there. But still, when people look through the PDF file, I mean, I can change the file name also, right? So we need to have some double check system or what, something like that. Okay. So, I mean, this is a normal thing, but I'm not sure. Okay. Does it make sense? Another point about cover page is to prevent some lecturer simply give marks. Maybe some lecturer just simply give a whole marks for you, no breakdown one. You know? So this is to prevent this type of thing to happen. So your cover page will have question 1, how many marks, question 2, how many marks, question 3, how many. But every time I will give you, right? Every subsection I'll give you this mark. How many? Then you know you get deducted how many marks. Okay. Yeah. Does it make sense? Okay or not? So please learn to be how to say, take initiative. Okay, 自动自发一点。OK 吗？自动自发，Yeah，这是其中一个我教学的原理啊，就是学生要学会自动自发，不要老师逼啊，还是扣你分啊什么的。然后真的没有必要，就真的要扣分，那种冥顽不灵的那种懂了还不要做那种那种是值得扣那种人的分。但是你不懂，你扣他分，for what？他都不懂，对不对？不知者不罪嘛。治疗还错那个真的要打了，对不对？好，Does it make sense？ 可以吗？OK 哈，Yeah。I think I will check when we hand in assignment 2 again. So we will check together. And both of them, you need to put the name into your feedback file and then submit again. Okay? Yeah. So that we don't get too many trouble. Right. Any question from last lecture? Any question or not? From last lecture? I half mark your assignment 2. I think doesn't look too good. Hopefully, if you don't understand, please feel free to ask or email me or come to my office hour. Okay. Please get help because I cannot cater for everyone's needs. So you need to calm yourself. Okay. Does it make sense? Okay. I can help you. Okay, if you want to help yourself. Please can't get help. Right. Okay. If no question, I think we can start now. So let's start our new topic today. So we're gonna introduce a very new concept here called Cosets. Yes. Hey, sorry. So we're gonna introduce a very new concept here, called Coset. I think you never thought about this kind of object before in your life, I think. Okay, so please try and listen carefully what coset is. So if you want to understand this concept, right, you can understand as CO, co, and then sets. Okay, so what's coset here? Prefix co plus set. So how do we define this coset here? So we'll start with a subgroup first. Okay, we have a subgroup first, and then we pick a random element in G. Maybe this A will live inside H, or maybe outside H. Okay, it's okay. Then we're gonna define what is called a left coset. Okay, so what's left about left here? Meaning we multiply this A from the left, AH. Okay, so you should wonder what is this AH here? Okay, so basically this coset is another set. Okay, so to talk about set, right? How to describe a set? I need to tell you what's the elements inside there. Okay, what are the elements looks like? So these are all the products A little h. So what's this little h? What do you think? It's an element inside the subgroup. Okay. So basically, what is AH? A capital H here. So it's defined to be all the element in G such that I can write G as AH. Okay, for some H in H. Very simple definition, but we're gonna do great things with this definition here. There's a lot of nice thing we can do with this AH here. So do you understand what this AH is? So what's AH here? Element in the group such that you can write it as A times some element inside your subgroup. That's all. Okay. So what can you what I want to remark here that this AH is not always a subgroup. Okay, it's not always a subgroup. Can you see why or not? Can you see why or not? It's not always a subgroup. Can you see why? To be a subgroup, what do you need to satisfy? Closure. What else? Identity. Inverse. Okay. What might not be always true? Inverse. There's one more obvious one. Huh? Two more choices. One more obvious one. Two more choices, right? What else? Inside subgroup, how many things you need to satisfy? I take away one already. Two more. I think it's more obvious one. Two more. Can choose. Choose again. Is the identity. Why? Because this A, you already taken. Okay, you take from G. If this A is E, then EH is H. But usually it's not E, right? Maybe it's other A. Okay. And this A will send E to where? A times E is what? A. Something is not A. Something is not E. Okay. So maybe there's no identity inside this set here, even. Okay, don't talk about inverse yet. Don't talk about closure yet. Yeah. Okay or not? Does it make sense? Closure, how to talk about closure if you want to talk about closure. So you want to ask yourself whether AH1 times AH2 is A of some H or not. Does the inverse of AH looks like A times some H. Also quite hard to satisfy. Okay, so in general, this is not a subgroup. Okay, so let's give some example of subgroup. So for example, let's give some example of coset. So if we start with any subgroup in G, so what is a coset here? H itself is a coset. H itself is always a coset. Okay, and then actually you've seen coset example before, but we never introduce it in this way. So what's the other example you've seen? For example, look at the trivial subgroup inside Zn. Okay, is it a subgroup or not? What's this? What's this content? What does this 0 bar contain here? Forgot了. What does this contain? Just 0, right? Okay. But if you write down the equivalent class, what does it contain? 0 and multiple of n. Okay. But what does it mean by coset? What are the other coset inside here? What can you do? What are the other elements inside here? Inside Zn? Other than 0. 1, 2, 3, 4, 5, 6, 7, up to n. So how do you construct coset here? You can take any n, any I, okay, and then add to the 0 bar here. So meaning what? So how many coset here? Then there are actually n coset. Okay, so what are these n coset here? So these are just 0, 1, and then all the way up to n minus 1. Is it? Okay. Does it make sense? Okay or no? Okay, so you can take 1 bar plus 0 bar, 2 bar plus 0 bar, 3 bar plus 0 bar, until n minus 1 bar plus 0 bar. So you get all these n concept here. Okay. Do you notice anything or not? Do you notice anything here? When you look at the number of this coset, right? What does it equal to? What does it equal to? How many of them? How many n coset here, right? How many elements in Zn? N. Okay. So there's not a coincidence here. So what you see here actually is, you can see that these coset, later we'll introduce this definition again, partition Zn. Okay. You learned partition before? Partition. The easiest example for partition is cutting a cake. Okay, when you cut the cake and distribute the cake slices, you are actually partition the cake. That makes sense? So you have a cake, and then you cut it, again, distribute it maybe among 4%. So you partition the cake into 4 parts. Okay, and then between these partition, there's no intersection, no non-trivial intersection. Okay, their intersection is 0. Okay, okay. Correct or not? 对吗？全部在想，对吗？当你分蛋糕的时候，不同的蛋糕是不是没有 intersection？ 有吗？没有啊。OK， yeah. 没有 non-trivial intersection。你的蛋糕就是你的，他的蛋糕就是他。对，因为已经 partition 过后了。没有，我们就 I mean, let me draw the partition for you. So you have a cat, right? So you can partition it into 4 parts, right? Maybe this one for Adrian, this one for Shaoxi, this one for Seng, and then this one for, I think Eric like to eat, right? So should give him. Okay, so you see, after you try to 4-part, right? Seng's slices don't have non-empty intersection with Adrian. Does that make sense? Okay. So this is called partition. So there's one subgroup that we interested a lot, which is the kernel of some homomorphism. Okay, kernel of some homomorphism. So let's say that. So let's say we have a group. Okay, we have a group, and then we have a subgroup here. Let's call it H. Okay, which is a kernel of some homomorphism here. And then with respect to this curve phi, right, we can form a bunch of cosets. Okay, maybe AH, BH, or CH. Okay. So in this case here, we can look at what happens, okay, to these left coset under the homomorphism, right? So for example, if I have a kernel here, what happens? Where do I send this kernel to? Huh? To the identity. Good. So to the identity inside the codomain here. But how about the other set? What happened to the other set here? Let's say AH here. Okay, so what is phi of AH? What? Mention phi A times phi H. So you need to be careful a bit. Here is what? A set. Okay, here is a set. But why I still can write down this equality as set here? Because when you consider AH as the element AH1, you also can write it as phi A times phi H1. So you collect all these H1 as a set again. But what do you get in this case? What is phi H here? This H is a kernel. Again, all of them will evaluate to identity. Okay. So to be precise here, I cannot just write phi A here. I should write phi A times a trivial subgroup here, because I want to write it as a set. Yeah, as a set. Okay, if I just write phi A, then I confuse myself, because these are, first of all, these are set. Okay. Okay, equal as set. So let me draw two here. Equal as set. So we need to use set notation. Does it make sense? So meaning what? Under this homomorphism, what? Where AH go? All the elements will get sent to the element phi A. Does that make sense? Okay, so if you look at all the other cosets, what happens? BH will get sent to phi B. Okay, phi B. And then C will go to phi C. Okay, no? Does it make sense? So somehow seems like the H disappear. It has to disappear because the H I pick now is kernel. Okay, so this is a choosing a specific H here. Okay, where H is the kernel of some homomorphism. Okay, does it make sense? Okay. Any questions so far? This is a quite important phenomenon to observe. Later we will see this again. Okay, so this is why we built this coset thingy. Actually, it's for this kind of kernel, for the purpose of this kernel. Okay. Right. So let's prove some proposition first, and then we'll see how it goes. So let's start with a homo. Yeah, homomorphism. Okay, a group homomorphism. And take two elements inside this group. Okay. And let's find the kernel of phi. Then there's three equivalent statement here. Do you guys know what is the TFAE here? The following are equivalent. Okay, TFAE. The following are equivalent. So what's equivalent here? Let's say if you have phi x equals to phi y, actually this is equivalent to saying that if you look at x inverse y, look at what happened to the domain element here. This thing actually live in K. Can you imagine? Okay, if fx equals to fy, yx inverse y live in kernel of phi. And then y is living in the coset of K. I think 2 to 3 quite obvious. Okay, try and think about first. And then 4, we can deduce that the left coset of yk is equal to s. Okay, try spend 1 minute to think about the connection between these statements. Do you know what is TFAE? Yeah. All the equivalent have to be if and only if. Okay, you can go from one statement to the other statement. Okay, I try to test this kind of statement in my midterm. What they do is they prove 1, prove 2, prove 3, prove 4. You cannot prove 1. There's nothing to prove here. You can prove only when you assume one of them is true. Then you can prove all the others. Okay, so TFAE meaning there's a if and only if condition between all of them. Okay, you can jump from one statement to the other statement. Does it make sense? Individually, these statements might not be true. Yeah. So you only can assume 1, prove 2, assume 2, prove 3, assume 3, prove 4, and then assume 4, prove 1. So this is one way to prove it. Okay, so one way to prove it is 1 go to 2, 2 go to 3, 3 go to 4, and then you come back. So can you verify that if we prove this loop here, you can go from any statement to the other statement? Do you agree? So if I have this loop here, how to prove 3 to 1? I can go from 3 to 4 first, and then 4 to 1. And then this form of loop, so you can start anywhere and anywhere. Yeah. Or maybe you can do like what I drew just now. So you can go front and forth between 1 and 2, 2 between 2 and 3, and between 3 and 4. You also can do this also. Does it make sense? So if you have if and only if for all statements, then you can go from 1 to any other. Really. Okay. But you see that actually this is the most efficient one, right? Because there's only 1, 2, 3, 4 arrow to do. Okay? If this one you need to do 1, 2, 3, 4, 5, 6 arrow to prove. So it depends on which one is easier, you can pick. Okay, so in this case here, we will do B. Okay, actually I will choose B to do it. You will see that maybe it's why is it easier. Okay, let's pick the B strategy here. And you can try A yourself if you like. But B here. So let's choose this strategy. So I can straight away go from 1 to 2 first. So let's remind ourselves what is 1 and 2. So phi x, I want to show that phi x equals to phi y, phi x equals to phi y if and only if x inverse y live inside the kernel of phi here. Okay. How about you tell me how to do it? If we start with 5x equals to 5y, what do we have? Huh? What can you do here? Okay, do. There's only one homomorphism here, right? So you should play around with this homomorphism. Okay, what can you do? Phi what? Phi inverse x. Okay, to prevent confusion, we will say phi x inverse. Okay, phi inverse x, you sometimes we will mention about the inverse of f. phi and then apply to x. But actually, we should take the inverse of this phi x. Okay. So we can take inverse to the other side such that we get identity on one side. But this is an if and only if statement, right? Because if you have a morph, actually not morphism, right? Here is just cancellation. Okay, cancellation law here. Okay. Or we can go here to here, also can go back, right? If I multiply 5x. And then what else? We can use homomorphism here, such that I get 5 of x inverse or 5y because 5 send inverses to inverses. And then I use homomorphism again to get 5x inverse and y is e. Does it make sense? So 5 send this element to identity. So x inverse y is living in the kernel of 5. Okay. So how about next one? Let's say 2 if and only if 3. So what's the statement here? So we want to show that x inverse y in k if and only if y in x k. Okay. So same up. You need to start from somewhere, right? So let's start from x inverse y is in k. So what does this mean? What does it mean by you are inside a set? It means what? It means that there's something inside k such that you are equal to that element. Okay. This is the definition, so you can go front and back. But what does this mean? This means what? You actually can write y as a x time k. But you can go back and forward also. And you just multiply x on the side. Cancellation law again. But what does this mean? This means what? You already write y as x time little k. Meaning what? Meaning you live inside the coset of x. Okay, definition. So if you like, maybe I keep this again. Okay, so top and bottom actually just a definition. Okay, and then middle is just cancellation law. Is it clear? Is it straightforward? Okay. Yeah. Right. Okay, so the last one is a bit tricky, so we should work it out slowly. So let's do the last one. So what's the last one here? So show 3 if and only if 4. So 3 if and only if 4. So what's 3? Let's copy down first. All right. So the last one here, don't you think very magical? Do you think it's very magical now? Why is it magical? Because once you know that y live inside the coset of SK, meaning what? If you build another coset using y, actually they are the same thing. Actually, this thing you see it before is like what? Choosing representative for your equivalent class of your Zn. Correct or not? For example, what? For example, what do you know? For example, let's pick Z. About pick Z5. Okay, pick Z5. If you look at the equivalent class of who, let's say 1, who lives in the equivalent class of 1? 6, for example. Z5 in Z5. Okay, let me write down. So I'll give you an example in Z5. Okay. If you look at the equivalent class of 1, Okay, what is inside this equivalent class here? You have obviously 1 and 6 minus 4, right? Okay, and then so on. Okay, but if you look at 6 plus 0 bar, right, you get 6 bar, but it's the same equivalent class X, 1 bar. Okay, so it's like you pick different representative, you still get back the same equivalent class. Okay, so you're seeing this phenomenon before. Okay, but how do we prove it? So we will split it into 2 steps here. Okay, so first, let's show y in xk implies yk equals to sk. So meaning what? You need to show set equality here. You need to show yk is in xk is a subset of sk and then sk is a subset of yk. Okay, this is the 2 things. But it's still easy. Okay, why is it easier? So suppose y is in xk here. Element, let's say element p in yk. Okay. And then somehow we want to write it as yk p and k. Write it as some x time theta k here. Okay. So what to do? If p live in the coset of yk means what? There exists a small k, let's say k1, such that p equals to y k1. Okay, this is the definition of coset. But what do you know about y? I can write y as what? S times some k, let's say k2. Okay. But there exists a k2 in k such that y goes to xk2. sk2. So p can be written as x times k2 times k1. But what is k2 times k1? It's still an element in k. Why? What is k? K is the kernel of homomorphism. Moreover, what? Kernel is a what? Is a sub. So it's closed. Okay, so this live inside X big K. Okay, since K is a subgroup. Okay. Does it make sense? Okay. Right. Can you imagine the other direction or not? Can you imagine the other direction? Let's say I take a element in SK. And can I write it as Y times some K or not? I think get someone to help me do this. Right? How can you want to try? How about the other direction? Let's start from an element in SK. Can I show it? I can write that element as Y times some K. How can you guide us step by step? Yeah, we can go step by step first. Just write down all the definition. Suppose K in XK, what does it mean? Let's say K3. such that. Good. Okay. And then, did you know about S or not? Do we know something about X or not? Do we know what's the relation between X and Y or not? But what? Okay, so what's our goal? We want to show that Q live in YK, right? Okay, but we know how to express K in terms of X already. So is there any relation between Y and X or not? Okay, so we would know that Y X equals to K2, sorry, I think wrong direction, right? Y times K2 inverse. Okay.
Y K2 inverse K3.
Okay. So is this Y? Why?
K2 inverse K3 is an element in the subgroup K.
Because
Subgroup K is all inverse and is closed.
good. Yeah, because K subgroup is closed under taking inverse, and then these two things are elements inside the subgroup, so it closed under these two conditions. Yes. Okay, does it make sense? Clear or not? Is it clear? Can you understand? Can you understand what you say? Okay. Okay. Or who don't understand? Yeah, so this is exactly what you need to do. So because K2, where is it from? It is from K. But K close under taking inverse. So this K2 inverse live in K. K3 live in K. But K is a subgroup. It is close under taking multiplication. So this the whole thing. Okay. Yes. Thank you. Okay, good. How about the other direction? I think the other direction will be shorter. So suppose YK equals to XK. What do you want to show? We want to show that Y live in the coset of S. Right. How to show? We already know that this is equal as set. Like last time, what I told you, right? Equal as set doesn't mean that the element. So let me write here. So by assumption, what do we have? There exists K1, K2 in K such that YK1 equals to YK2. Okay, so because it is equal as set, it doesn't necessarily mean that this K1 and K2 has to be the same. They might compute. Okay, it might compute. Because it's just equal as set. Okay, so meaning what? Meaning YK1 here is something inside SK. Hey, sorry, this one is X. XK. Okay, so it might be equal to some other K2 times X. But is this enough or not? Is this enough to show that Y is in the coset of X or not? Is this enough? How? How, Lydia? Because we can write what? Y as a SK2 times K1 inverse. Again, this thing is living inside XK. Same reason just now. Okay, close taking under inverse, close taking under multiplication. Okay, does it make sense? Okay, so proof actually not hard, but you need to appreciate these four statements here. Very, very, very important for your life. I mean, okay, not for your life outside, but life inside this class. Okay, to survive in this class, you need these four statements here. Okay, So once you know that two elements equal under the homomorphism, actually x inverse y is in the kernel. Okay. Can I swap x and y or not? Let me test you. Can I swap x and y? Can or not? Can. Can, right? I just move what? Py the other side. Any side will work actually. Right or not? Any side will work. Okay. Yeah. So actually there's a lot of permutation you can play here. X inverse y, xy inverse, y inverse x. Right. What's the last permutation you can do? Y x inverse, for example. Okay. Yeah, all these permutation will live inside K. And then 3, so you can also say that x live in YK, for example. You can try and prove it. And then last one, there's nothing to play. Must be YK equals to SK. Okay, no? So you can jump from the first one to the last one also. Eh? Jumping from the first one to the last one, isn't it what I drew to you just now? Isn't it what I drew to you just now? Where this coset goes out under phi. Phi y and phi x. But they are the same already. So their image have to be the same. Does it make sense? Okay, try to appreciate these equivalent statements. Very important. Okay, let me say a few more words and then we will take a break. So next. So next is position. Let hash again be a subgroup. Then I'll say that the left coset of hash in G are equivalent classes. Okay. So whenever we talk about equivalent classes, we can define the equivalence relation. So what's the equivalent relation here? So we'll say that two elements is the same. Okay. If B equals to A times H for some H in capital H. Okay, so prove that this relation is an equivalence relation. So meaning what? You need to prove that it is reflexive, transitive, and symmetric. Can you quickly think about it? Why is it reflexive? Why A equals to A under this relation? If A equals to A, what hash you need to take? Identity, no? Does your subgroup has identity or not? Not. Okay. If A equals to B, why B equals to A? Huh? Identity? Not quite. So yeah, taking inverse, good, very good. So if B equals to A hash, this implies what? Then I can write A equals to B hash inverse. But hash inverse should live inside my subgroup. Transitive there. If B equals to A hash, C equal to B hash, so possibly different hash, then what? Can you write C as some A hash or not? A of some hash or not? A H1, H2, good. Yeah. Okay, so it's transitive. So this is an abstract nonsense. If you have an equivalence relation, you have equivalent classes. And then after you have your equivalent classes, these equivalent classes will partition your set. Okay, so this equivalent classes will partition your set. Do you know what's the formal definition of partition or not? No. Huh? So you should imagine the cake cutting process. Cake cutting. So let's say you have a collection of set, subset, okay? Collection of subset. Will partitions the original set if what? First of all, your cake must be the union of these slices. Correct or not? Okay. If you want to partition your cake, if you add all the slices together, you should get back to your original cake. Okay. And what else? Adrian portion must not be the Pansing portion. Okay, their intersection is empty. Okay, for any pairwise portion. Okay. So in other words, sometimes people will write like this. So people will write like this. A is a union, but the union here we put this like this union. Okay, union, disjoint union we will say disjoint union from I equal to 1 to n of ai. So this is what we call a disjoint union. So when people do this, it means that the intersection between pairwise set is empty. Okay? Usually you put the cup, right? The big cup. Okay, but this one is not sure how to call it. Square cup. Okay, square cup. So corollary says what? So corollary is the left coset of a subgroup H of a group will partition the group. Okay or not? So let me draw the new group photo for you. So last time when I draw group for you, right, we look for some subgroup, right? But this time we're gonna partition the group now. So we're gonna partition it into, let's say, 4 slices here. Okay, so we have, let's say, H, AH, BH, and CH, for example. Okay. Let's say I pick my H to be G. What's the partition here? Let's say I pick H to be G, the whole group. G is a subgroup of itself, right? So what's the partition here looks like? What is AG, BG, CG? If H is equal to G, how does this partition look like? If I take H to be G, yeah, it's just the whole group, the whole cake. Because if you take A times G, you are just permuting the whole group element again. Correct or not? Because inside your G will have a inverse. So when A meet with A inverse, you will create your identity again. Actually, you are permuting your group. Okay, so if H equals G, AH is G, CH is G, and then BH is still G. So it's just a whole cake again. So you should imagine that this subgroup is a knife. This knife is gonna partition your group. So you use H to cut your group. Okay, once you have a subgroup H, you can form all the concepts, and then you should partition your group. So actually, subgroup is a knife here. Okay, once you have this knife, you can start partition your group already. Does it make sense? Okay. Any question so far? Any question? No? Okay, so let's take a break until 8:11. 抄哪里？这边。他记得吗？没法一边听课一边讲，为什么？脑子转不过来了。你不能让我的脑子同时兼顾群了和 LaTeX 好不好？哎
proposition 刚刚那个 proposition 讲这一个菜，如果是10分的话，4个会是
也是的。
但是如果你的 H 就是上路的话，它就不可以是个可能。所以正常情况下是不是？是你要是能说，
我知道龙门，我知道龙门。
但是你正常的上路不一定是 normal 的嘛，所以这个不是正常情况下的。但是哦，后面这三个不是可以不一样的，
只能说如果
可以是一个 homomorphism 的可能。
我们还没有到这一步，
它已经定义了 H
我们还没有到那一步。可能你可以说我们可能在用这个某一个特性，我不确定，但是就然后你要讲
对，正常情况下，这一个 phi A 的 phi B 这个 homomorphism 定义不出来的，所以应该只有如果 H 是普通的上路的话，应该走后面这个是成立。
啊，你是说如果是掉 H 是可能
这里面我们
我证明没有用到可能，
我觉得可以啊，因为你刚刚的证明只有大二用可能，其他三个是没有的，其他直接就没有用到。
这样其他都能用，只有第一个第一个做不出来，其他都还是
确实，对，因为只有他刚刚证的时候只有第一个用到了，后面都是其他都没有用到，我的观点。
确实对，然后
就确认一下这一个东西吧，因为我怕我自己想出来会错。
想
就是他刚刚说的呀。
我怀疑这个去掉另外三个应该是没问题的，在 H 不是
没有啊，你怀疑的时候你就可以看 program 了。program 的时候如果没有用到特性，再拿出可以。我想一下呀，因为我 prove 的方式是这两个跟这两个，对比较obvious 一点。因为如果你是 prove 这种绕着的话，那你绕着的
中间差一环就会要重新来过。
对啊，你就重新来过，你只会有降罢了，你就这条线嘛，你就回不来。大家好，我是这样子 prove，所以你可以评价某一个来中间还有一个。
OK，这样就没有讲这个
了解。那个谁做？等于啊，sorry， 要等于是吧 ？OK， 要等于对。全部人去上 PDE 咩？怎么全部人这样累？啊，来看看，没看我的朋友。你算呀？还有什么？哦，彼得。没有啦，是看那个老师要放什么东西进去吧。我们那边也有两种 PDE，
他讲他影响很
没有啊，
放大也是蛮大。
它可以单算罢了的那种。嗯，确实。
那边他拿
小杨，哎，红杰跑。
澳洲分 chapter 这件事，我们整个学期只有 ring 和 group 两个 chapter。
对，
就或者像两个 chapter。
对
，new group 一个人。OK， 再加上他们的 chapter 里，你不觉得太少了吗？
一天要100多遍，我感觉加他要200遍。
谁让你讲那么多，弄得我打都累。那就付功夫。
对，不要这样说，有付，只是不能一直付吧。还没有，没有这样快嘛，东西还没有做出来。
那个动力都没有。
对啊，把这个海底捞答应下来，我们就有动力了。
海底捞我觉得还是太我的budget以外。
我觉得挺多。
OK 啊，
我们只有6个人。
100块啊，500-600。
我的也肯定不会亏待你的，不要担心。
当什么打字员，可能都不比这个高，我觉得。
没有啊，这个我们是很自动的，自愿。可以啊，我不会亏待你的，相信我，我不会亏待人的。志明
你老
啊，
这边老的。
你也想海底捞？喂，你先别还我，你先别还我。
倒闭。
还有莉迪亚，
然后你要提醒我，没忘记。
对，还有莉迪亚，志明 ，OK，曾子航，Adrian，嘉玲、子轩、莉迪亚、嘉玲、邵琪、Eugene、Jasmine、Albert、陈斌、金鱼、超金鱼 ，OK，金鱼，陈浩瑞、曾子豪、艾辰、何心怡、修彤，呀，冰夏，冰夏，小月，I think not here，哎，小月 here，冰夏 not here right？冰夏，OK，第三个，刘子涵，OK，洪瑞、宇轩，呀，孙佳怡、方瑜、佳怡，呀，苏瑶、云溪，常云，OK，严正、陈一凡、钟一凡，哎，不是钟一凡，康平、赵胜、men春、昊天、金星，OK，一航啊，2990。68695980，修着。哎，我也是一航啊。Lim一航 is the one sitting front 啊。OK。Ray Shaw，韩星、林恩、伊恩，OK。郑月、赵瑞、金鹏、刘金鹏来听东西啊。Search me 啊。C，有没有 search？韦泽，OK，林晶，Yep。Hey, usually your class I sit in the A4G09. Can you guys achieve one seat and then left another seat or not? You know what I mean? So if you sit what? Yeah, 左右是空的 beside you is empty. Is it possible or not? 不够啊，不够啊。那你们平时考 midterm 是怎样考啊？什么？坐在一起跑？哇哦！要 integrity。哦，有 integrity。OK。
眼睛看到答案都可以删掉。
这样也很奇怪，这样哦。想一下哈，在想会不会需要分两个班？确实分不了。For the midterm, you can start prepare already. You should prepare a cheat sheet, A4 cheat sheet handwritten 不要 print print 的就当场撕掉只可以用写的手写的，我们用人力来限制，不要依靠科技 ，OK？ 我们手写手写 ，Yeah， 考试范围我们应该这周或者下周我就要跟你们讲。 two-sided A4 two-sided，OK，A4 two-sided。呀，给你尽量抄多一点进来，但是不要 print 啊，不要用电脑打印或者什么，也不要贴什么 sticky note 在上面啊，不要做这样夸张的事情，好不好？就对，就单纯的 A4 paper，然后就是用手写 ，OK。I will send out a notice again. Does it make sense? Okay. You can write how small you like. Can. No printing. Okay. You can write. Both sides, yes, both sides. Okay, both sides. Yeah, both sides. Okay, you can copy whatever you like into the. 希望不会太难。我尽量不会太难，尽量不会太难。关于难度的话，如果你难不要哭啊，不要哭。但是因为就是大家都会觉得难，所以不用怕。不要哭，不用哭，就尽量想讲做就好不要哭没有空哭我们没有空哭要尽量想的如果你不会，你同学应该大多数也不太会，所以你不用怕没有，
不会就是不会。
没有想得出的，一定想得出，一定有理由想得出。OK， 数学好玩的点就在这边，就是你想一想，应该就要想出来。有逻辑的会不会考满分？可以挑战一下。我感觉数学系还没有一个人考过我的考卷考满分，挑战一下。别个系的有考过我的考卷满分，就是不是数学系的。I mean for 他们 standard 他们得到他们的100分嘛。就这个就数学系目前还没有，希望可以在你们的班产生。我对你们班有希望。至少你们的态度正确，一切都正确了。分不是很重要啦，哎呀，分不重要，重要是你们之间的排名，其实这个比较重要，就是说你在你的班的前几或者几把线，这个比较重要。OK， 喂，外面怎么这样暗哦？也太神了还有人呢。OK， so let's continue. So lemma is 这把刀其实切到很准。Okay, what do I mean by very accurate here? So all left coset AH of a subgroup H, okay, from a group G actually have the same order. Okay, meaning what? They have the same cardinality. How to show something is the same cardinality? You know or not? 你怎么知道两个 set 的数量是一样的？你知道要怎么做吗？你可以去算OK， 你也可以去 show left and equal to greater or equal to. But the most direct definition is what? There exists a bijection. Bijection 就解决了，因为你又要考虑 infinite 的问题，又要考虑 finite。infinite 的话怎样数得完呢？ Bijection 就解决了。There's a one-to-one correspondence between two sets. Okay, so it follows from the fact that actually there's a bijection between the subgroup with any coset. What's this bijection here? Very simple one. Okay, in algebra you need to learn a skill. Whenever you want to build a map between two sets, there's one obvious map you should consider first. For example, in this case here, you know that I want to build map from H to AH. So what's the obvious map here? So whenever you talk about map, even you want to define about map, right, you need to learn about the element inside of set first. So H here is what? Little H. A H there? A little H. So how do you relate H and A little H there? You can send H to A little H. Do the obvious thing first. If it works, good. Finish, done. 可以交卷了。没有啦，要 proof 一点东西再讲。OK，so 不要去想那种有的没有的 map 出来啊。先 first try the obvious one, most direct one, whether can work or not. 我不知道 ，try 先 prove 它先。OK，so we want to show that this map is bijective. Do you agree that once we have shown this, we will know that all the cosets will have the same cardinality? Do you agree or not? Like BH, CH, DH, all have the same cardinality. Follow from this statement here. Do you agree? Because you can link all the CH, BH, DH back to H. Okay. Use the same argument here. Okay, so again, show bijective or last week I told you, right? There are two ways to show a map is bijective. One way is to show that this map is onto and one-to-one. The other way to show this is bijective. Find the inverse. Okay, let's do one way and then the other way I left as exercise. Which one you think you are not good at? And then we will try that. You want to find inverse of this map or you want to show one-to-one? Huh? Two 啊 ？OK 啦，韩信都讲 two 了。OK， 好好听啊，我讲两个啊。OK, let's do two then. So first, we will show that it is one-to-one and onto. How we make everything small so that we don't go to the next page. Everyone can remember the statement here. Okay, so let's do one-to-one. One-to-one says what? Suppose what? Suppose MA of an element H1 is equal to the MA of another element. And then you want to show that, sorry, H1 equals to H2. But what does this imply? What is MA of H1? What's this map? AH1 equals to AH2. So by cancellation law, you get H1 equals to H2. Good, done. Okay, how about onto it? Onto says what? You need to take any element inside your domain. Right? You want to find, so you want to find find what? Want to find, how to put it up? Want to show that there exists an X in H such that MA X equals to Y. Correct or not? Okay, so you do working first. Okay, in this case, answer already give you already, meaning you need to satisfy this. But to satisfy this, what does it mean? This means that A times X has to be Y. So this implies what? X has to be A inverse Y. So in this case here, we will take X equals to A inverse Y. So that what? So that what? So the MA of A inverse Y equals to A times A inverse Y equals to Y. A bit dangerous, right? Is this A inverse Y live in H or not? What is H? Is it living in H or not? You need to settle this problem. Is it living in H? What do you know about Y? We haven't used Y property, right? Y is what? Things Y equals to A of H1 for some H1 in H. So what is X actually? Actually, X equals to A inverse A H1, which is H1. So it has to live in H. Okay or not? Okay, does it make sense? Okay, so you see, in algebra is, I would say, easy proof. Why is it easy proof? You need to use all the assumption that I gave you. Once you use all of them, then you have proven all of the stuff. Okay, no? Okay. Right, so we are using this assumption here. Y is in AH. So we are really taking something inside H. Okay. What's that thing? That thing is how you realize Y inside AH. Okay, it's the H that realizes this Y inside the coset. Okay. Okay. How about inverse? So if you want to do inverse, you need to define it. So the hard thing about doing inverse is you need to find what's the inverse here. So how do you define MA inverse? Do you have any idea? First of all, do you know this inverse go from where to where or not? Go the other direction. From where to where? AH to H. So what's the nice choice here? What's the nice choice here? You need to send something look like AH to something, some H. What's the nice choice? Nice choice here. A little h to little h. Like this. Like this. Because I asked you to do the obvious thing first. Okay, maybe we try. 可以吗？我们试错，大家可以吗？可以允许错吗？可不可以？可以啊，允许错啊。如果对就好哦，错的话不要太伤心啊。OK， OK， 可以吗？ We go through mistake together because when you do assignment, you also go through mistake, right? But you don't know how to fix. So the difference between you and me, there's only one difference only. Sure, I got experience. I got experience how to correct mistake. You don't have. You have mistake, you don't know how to correct. You just close the book and then go to sleep. Okay, so now we go through this mistake and then we learn how to correct mistake. Okay or not? Okay, all right. So let's see. Let's see. So if this is a inverse, right? What do we need to check? We need to check two direction, right? MA and MA inverse and inverse and MA. Okay, so if you do MA inverse first, you should add on A of little h like this. Okay, so by construction, what do you get? First, you get M of h. Then you get what? AH again. Identity of AH to AH. The other one, if you start with H, then what? You do MA inverse AH, and then you do H. Seems okay. Seems okay. Good. Seems okay. Yeah. Good. Yeah. Right. Because this is not required to be homomorphism, so be okay. 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 Cool. Good. Right. So so we know more now. Okay, what do we know more? We know that all the partition here have the same order. Okay. So if H have 4 elements, all the cosets should also have 4 elements here. Does it make sense? So this knife cut equally. Okay, the subgroup will cut equally here. Okay. Does it make sense? Okay. By the way, this picture is where the why this is why our arting solution there's a watermelon there, because I keep drawing this kind of picture for them last time. We're cutting partition. The watermelon. Why is it watermelon? Because you see, if I draw these elements, it's like a seed inside a watermelon. Okay, so there's a watermelon picture inside there. So the watermelon in the arting solution is actually partitioned a bit. Okay, it's not a random watermelon there. Not because we like to eat watermelon, but there's a deeper meaning there. Okay. So meaning from here, meaning what? Meaning if I know the order of a subgroup, and then if I know the number of cosets, meaning what? I can recover the number of element of the. Can you imagine or not? So what's the total number of element in this group? 16. How do you get 16? Yes, 4 times 4. Luckily, you don't tell me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, seriously, this is what people tell me when I first taught this class, So they're really calculating mind one. They go one by one, one by one. Yeah. So this is a higher level of multiplication. Why 4 times 4? You are taking the number of the order of subgroup times the number of cosets. Does it make sense? So these 2, 4 have different origin. So we'll make this concept precise here. So let's define. So again, we have this subgroup here. Then the number of left coset of a subgroup is called the index of H in G. Okay, so how do we denote this index here? This index is denoted by square bracket G and then semicolon H like this. Okay, so the number of left coset we call index and then denoted by left coset not because we multiply G from the left or put G at the right. Does it make sense? So the theorem that we just discovered just now, which is you have proved this theorem. This theorem is called a counting formula. We have element order of G is order of H times this left coset. So how to prove this? How to prove? We know that the left coset partition G, and then we know that every left coset has the same elements. These two facts together prove this theorem here. Understand or not? So we know that, okay, let me repeat again. So now is your turn to learn how to go from a concrete calculation to abstract explanation. First of all, we write G as what? As all the coset, as the sum of all coset. Correct or not? Okay. And it's important that their intersection is empty, so that you no need to take away the intersection element. Element live in the intersection. Correct or not? I mean, you have a formula like this, right? So remember, recall the cardinality of A union B is what? Is cardinality of A plus cardinality of B, take away cardinality of A intersection B. But we know that their intersections are 0. Okay, pairwise 0. So what? Moreover, what do we know? All of them has the same value. Okay, meaning if you want to add all of them together, you simply just take the cardinality of H times how many of them, which we define as the index of H. Okay, yeah. So this is a step where you go from practical to abstract. Okay, how you explain very calculation stuff in an abstract manner. Does it make sense? Any question? Question? Feel free to ask. So this is counting formula. But from here, what did you observe here? We write G as a multiple of H. Is that a multiple of H or not? Because the index here surely is natural number. Okay, so we write cardinality of G as a multiple of H. Meaning what? So this is the famous theorem, what we call the Lagrange theorems, which says that if G is finite and H is a subgroup, that is finite, then from the theorem above, we know that the cardinality of H will divide the cardinality of G. Okay, how does it divide? The cardinality of G is equal to the cardinality of H times the index of H. Okay, number of left concept. Okay, does it make sense? What are you thinking? Any questions? Okay. Ishan, are you following? No. Huh? Do you have any question? Do you have any question? 啊？什么？啊，听不到，为什么？你再想一下。哦，I mean，应该没有什么东西好想。sorry，我没有什么要冒犯你的意思，但是我就想说，sorry 啊，没有要冒犯你的意思啊，sorry，但是我只是说，OK，再来一次，说 sorry，没有，sorry，因为怎么说哈，我们应该要保持我们在同一个节奏的当中，不然的话我们很常会 off tempo，所以我现在要告诉你的是，我没有在让你想东西。我在我会有时候会让你们想东西，但是有时候我没有让你们想东西，就是说这个东西应该是大家都要同一阵线知道的。所以如果不是同一阵线知道的话，就是说我可能不知道你不知道了什么东西，这样就有点危险，所以 let's try we have to understand these two statements at the same time because 这里其实没有什么很难的东西，让我 copy 一下。因为如果你不知道的话，就是代表你已经有一些 definition 已经不是很清楚了，所以我们再 back up 一点。喂，中华不要给我 copy 好吧？那我就记抄啊。真的没有我换错啊 ，sorry 啊呀，divide G， 这 divide G。对，哎，我犯错方向了。对，方向对啊。OK。Wait counting formula says what cardinality of G equals to cardinality of H times the index。看得到吗 ？I mean, let's say 如果你这个看不到的话 ，maybe 我放一个 example， 对不对？let's say 2除4 ，OK，the other one 呢？4等于2乘2 maybe。但是这些号码现在有意义的，它是某个 subgroup 的 cardinality。These, everyone see these two statements here with this example. So these 4 here will represent the cardinality of 4, and then 2 will represent the cardinality of 2. But to make 4 equals to 2 times something, the index here has to be 2. 玉仙怎么样？有问题吗？对啊，不好意思啊，问罢了。所以你刚才卡在什么部分？我真的很好奇，因为如果不懂的话，下次还是会有。刚才卡在什么地方？还是哪一个 definition 不明白，还是哪一个贴的肌肉而已？哦，什么是 cardinality？Yeah， 这句话不懂真的是整个堂都听不懂了。cardinality 很重要。What is cardinality？Cardinality of a set。OK， 这是 set 的一个特性。所以什么叫做 cardinality of a set？ 就是 the number of element inside 那个 set， 对吗？来，所以刚才卡在哪里？不啊，就纯粹没有明白了。哇，越来越伤人了。所以，真的不知道。我其实很好奇这些点，因为我需要抓这些点 ，otherwise 下次还是会有人听不懂。因为真的没有什么特别的。真的啊，不是 ，I mean，OK， 我不要解释太多，就是这个标准来说，这个是没有什么特别。So I think sometimes I need to align to your expectation. You also have to align to my expectation. 或者是互相的，我觉得不能我只跟你们靠拢吧，因为对嘛，不可能嘛，你要向我靠拢嘛，我们互相靠拢的，对不对？啊，Yeah，OK，可以吗？合理吗？我们互相啊，对不对？不会只有一单方面付出嘛，对不对？这样太累啊，对不对？是不是？哎，我觉得你们这边的人谈的恋爱比我多哎。SMUN 出名谈恋爱，我第一次看到他这么多情侣在学校走来走去。Anyway，这是 side story。But OK，any question or not？ 这两个 statement must get it 啊 ，you must get it。OK，nothing special here。OK，so I mean，there's a strong corollary here。OK 啊，所以这个才要想，这个就比较难了，这个才要想。So corollary， we can relate this result to the order of an element of a finite group. Okay, we can deduce that order of an element actually divides the order of the group. See, this is the first time. Sorry, careful. This is the first time we combine the two different order together. Still remember or not? What is order of an element? Your assignment already passed out. What's the order of the element? The smallest positive integer such that a to the n is identity. But order of the group is the cardinality of the group. This is the first time we put these two words into a same statement. Some number that makes the element to identity can divide the number of the cardinality of your. Okay, no? Seems weird, no? Quite weird. Okay, seems weird. Quite weird. But can you build a subgroup using this element or not? What's the obvious subgroup that containing this element here? Yeah. What can you do? If you take G be a group, what can you consider? Just consider any X inside a group. Then you consider the cyclic subgroup. Okay, you consider a cyclic subgroup. But what does the previous theorem tells you? Sorry, cyclic subgroup generated by X. So what does the previous theorem tells you? By Lagrange theorem, all the cardinality of all your subgroups should divide your group. Okay. Since G is finite, if G is finite, what number can divide a finite number? All the factors. Okay, all the factors. So meaning the cardinality of the cyclic subgroup is finite too. Okay. If it is finite, meaning what? This is a cyclic subgroup. Meaning what? It must go back to identity with what order? X have to go back to identity with what order? What's the order? Can you guess? What's the order? No, G too big. G may be too big. The smallest one. 1. No, if X is not identity, then it won't go to identity with power 1. 0. 0. No, we define X to the 0 to be the identity. It is always 1. So you need to pick a smallest positive integer. Just take the cardinality of the subgroup of X. Yes. Okay, so this is the order of your X. So if I want to write it clearly, it means that X to the cardinality of the subgroup is equals to the identity. OK 了，很奇怪吗？你觉得很奇怪吗？来给 example， 来忘记 example 啊。其实你们没有注意到这个点。For example 什么？cyclic subgroup in let's say Z6。OK， sorry 啊，应该不可以用这个 element 哈，is a subgroup。So how many elements inside this one? 0, 1, 2, 3, 4, 5, 6. And then how many? What's the order of 6? What is the order of 1? So no 6. Yeah, thank you. So what's the order of 1 here? 6. Because 1 plus 1 plus 1 plus 1 plus 1 plus 1 is 6, which is 0 more 6. Okay. And then 6 is the cardinality of the cyclic subgroup 1. Okay. Does it make sense? Okay. Yeah. So actually you've seen this before, but we write it abstractly. Okay. Okay, so if you take any number less than 6, you won't go to 0, 1. Correct or not? 1 plus 1 is 2, 3, 4, 5. Okay, all of them is not 6. Yeah, all of them is not 6. Yes. It's not 6, then it's not 0 in Z6. Okay or not? Okay. Right. Right. So meaning what? So the order of an element of a finite group divides the order of the group. So another corollary. So whenever we talk about this division, you must be sensitive. Sensitive about prime number. Because what is prime number? Do you know about prime number factorization? So every number can be split into prime. Why? How do we define prime? Prime is a number such that only one or itself can divide it. Okay. So let's say let's say our group is a cyclic group of order P, meaning what? who can divide this P if it is prime? It is either 1 or P. Okay. So the order of elements in a cyclic group of prime order P is either 1 or P. Meaning what? If you go to a cyclic group of order prime order P, if you go and build cyclic subgroup, the order is either 1, so meaning it's the trivial subgroup, or again the whole group. You get the whole group back. Okay, so this is the example that I showed you last time. Every group of prime order is isomorphic, and then they're isomorphic to cyclic group. Okay. So disprove it. Okay. So I mean, in principle, you can prove this. Let me see corollary. So suppose that a group G has a prime order P. Let A is not equals to E in G. Okay. Then what? Then this G is the, okay, just say G equals to the cyclic subgroup generated by. Okay. So I put a stronger statement here. Whenever your group has a prime order, it is a cyclic subgroup generated by any element inside your G, which is not the identity. The identity will generate the trivial subgroup. But if you take any other non-trivial element inside your G, you can get back the whole group. Just take the product. Correct or not? Generate means what? Take the product of the elements inside here. So this is the only generator, A. So you should do A squared, A cubed, A4, A5, A6. Does it make sense? Okay, before I prove to you, maybe I give you example first. For example, prime order, easy one. Pick what? Let's say Z5. Okay. And then this theorem tells you what? Z5 equals to the cyclic subgroup generated by 1, equal to the cyclic subgroup generated by 2, equal to the cyclic subgroup generated by 3, 4. Yeah, go and compute it. Is it true or not? True or not? Think about it. Think about it. 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. And then 2 plus 2, 2 plus 2 plus 2, 2 plus 2 plus 2 plus 2. And then 3 plus 3, 3 plus 3 plus 3, 3 plus 3 plus 3 plus 3. And then 4 plus 4, 4 plus 4 plus 4. And 4 plus 4 plus 4 plus 4. Do you get all the elements or not in all these calculations? Go and compute. Okay, you should get all the elements inside Z5. Okay, I don't write the last one because if you write the last one, obviously it should be 0, right? Because it's a multiple of 5. Okay, so these 4 should represent the other 4 non-trivial elements inside your. Okay or not? So after you see this example, you should think how to prove the statement here. Okay. How about prove this and then we will finish our class. Yes, let's prove this. Right. This proof is quite important. Okay, this is a contradiction proof, which is a very important proof technique you need to learn in this class. Let's say there will be 2 versions of proof I will give you in my lecture notes, but I will only do one in this class. Okay, let's do this one. So proof. So you see, What's the statement you want to get? Equal as that. Okay, equal as that. So you need to show left, right inclusion. Okay, left and right inclusion. So let's start. So let's pick an A that's not equal to E in G. Okay, where G is a group. First of all, which inclusion is easy? Which inclusion is easy? This one you should determine now. Which inclusion is easy? Left to right or right to left is easy? Sorry? Left to right or right to left? Which one is a subgroup of which? Huh? What? Right to left, right. Why? Because cyclic subgroup is already a group. Moreover, where do I get the A from? G itself. Okay, so G is closed under multiplication. Okay, so we will say that we know that the cyclic subgroup is in G, right? As A is a subgroup of G. Okay, then we need to show the other case. The other case says what? If I want to go from G to this cyclic subgroup, what do? I need to write everything in G as a power of A. Okay, how do we do that? How do we do that? So here is the trick. So here's the trick. So suppose G is not a subset of A. Okay, meaning what? Meaning there's something inside this G such that you cannot write this element as a power of A. Okay, if can, then you are done. But suppose you cannot. But what do we know about G? We know that our G is finite. Not just finite, we know the cardinality. The cardinality is prime. Okay, this is how we set up our corollary here. Hence what? Okay, what am I trying to do here? Let me think. Am I doing crazy stuff here? It's contradicted. Order up. Hey, what am I doing here? What's my X trying to do here? Why get crazy here? Okay, let's think again. What time is it? 8:55. Okay, let's give us 10 minutes. Huh? No, I mean at most 10 minutes. If we cannot solve it, we leave to next one. Okay, let's think about it. I think there's some gap here. So let's see how we're gonna do this. Let's see. So let's back up a bit. Let's back up a bit. So let's write down what we want to show. We want to show that G is a subgroup of A. So for everything in G, we want to write it as a power of A. Okay. I think there's no way to do this now first. So let's assume otherwise. Okay, so suppose otherwise. So I think here should be a contradiction. Suppose that for contradiction, this is not true. If it is not true, that means that there is an element in G such that X is not inside the cyclic subgroup, meaning that I cannot write it as the power of A. Where do I get the contradiction? Let's think. Is this a false? What am I trying to say here? So how do I link this X back to A? So this P is quite important here. Any idea? Try and think about. Any idea? Can we use this path or not? Any idea? Yeah. Try and think. P is prime, yeah. P is prime. But somehow I think there's a gap in my argument here, but to link this X back to A. Oh, wait, let me see. How this thing will create contradiction? Let's see. X is not inside A. This thing, do we know about A? We don't quite know about A. But we know that the element of A must divide the order of A. Okay, so let's continue. So we know from previous corollary, what do we know? So what do we know? The order of A. So the order of A. Hey, some of you are write these are the order of A. I think I never introduced this. I didn't put this bar beside element. I only put bar for set. Okay, so don't do this. So the order of A will divide P. Okay, will divide P. But we know that. We know what? What do we know? We know that the order of A cannot be 1. Because it is not a identity. So since A is not the trivial element, the order of A must be P. Okay? Must be P. Do you see some contradiction here? No? The order here must be P. This means what? This means what? Wait, slowly. This means the order of your subgroup should be P. But you say that there's something in G not coming from A means what? You have an extra element. But G contains what? This subgroup union an element X. So the cardinality of G is greater or equal to P plus 1, which is not a contradiction here. Okay, no. But actually, there's one thing to prove here. There's one lemma actually. How do you see that this cyclic subgroup must be order P? If I know that the statement is like this. If I know that the order of my element is P, why the order of my cyclic subgroup is also P? Okay, so maybe I can put a lemma here. So lemma here is, so here is done. Here I put here done, contradiction. So let's look at the lemma statement here. So what's this lemma here? So lemma. Okay, this lemma is what I refer to a very important proof technique you need to learn here. So lemma, if A has order P, not just prime or any order, but then what? Then the cyclic subgroup generated by A is also order P. Okay. Does it make sense? Okay, this statement deserve a proof. 它需要一个证明。Okay, 它需要一个证明 deserve a proof. So I mean, obviously you can build this subgroup, right? Is A square, A cube, A4, A5, FC, A7. But why in principle they have to be distinct? Why they have to be distinct? Okay, maybe one obvious observation you can make is because you already said that P is the smallest positive number that equals to identity, so you want equal identity first. But now I'm asking you, why all of them have to be different? Not just different from identity, they are distinct from each other. Okay, so why? So this statement deserves a proof here. So, well, let's prove it for our last course here. Last course for the night. So why? Suppose it is not. Okay, so we prove by contradiction. Suppose that for sake of contradiction, maybe so what's the contradiction? Maybe some power equal. Okay, maybe some of the power equal. Okay, for some ij less than p. Maybe they equal during some power. Okay, maybe. But this implies what? This implies that A times j minus I equals to identity. But this means what? This means what? You have two integer less than p, and then you take I minus j is an integer less than p again. So you get to p earlier. Meaning what? Since j minus I is less than p, this contradict that p is the order of A. Hello? 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 Okay, I'll finish soon because there's a club I need to go. They have orientation tonight. Okay. So, okay, does everyone follow this? Okay, so meaning if you agree, meaning you should collapse your cyclic subgroup already. You should collapse it. If you turns out that they agree at some power, you should collapse. Collapse to this j minus I. J minus I is actually the order, not the p. Okay. Never mind, I'm going soon already. Okay, right. So I will see you on Thursday. Hopefully, I can return your assignment. Then we will discuss on Thursday.